All right, this is the next video for Unit 1. Today we are going to talk about something called a velocity time graph. This is another type of graph that can be used to analyze motion. And here is what it looks like. Here's my vertical axis, and I'm going to draw the horizontal axis in the middle. And what we have is velocity, or v, and time, t. So above here, that's a positive velocity. Here's a negative velocity. Positive velocity would mean that we're going forward, and a negative velocity might imply that we are moving backwards. That's the positive and negative as it applies to velocity. So let's sketch some velocity time graphs of the following motions. So uniform motion, moving forward at a slow speed. Remember, uniform motion means constant speed. So here's our velocity time graph. I'm going to draw my axis here. Here's my x-axis. Velocity v. So let's say there's 1, there's 2, here's -1, and -2. Here we have time, which is t in terms of seconds. And I guess I need to go back and make an adjustment. Change this velocity v. Velocity is v, but the units are meters per second. There we go. So we are going in uniform motion, which means a constant speed. So let's say that I start at a velocity of 2 meters per second. If I am moving at a constant speed, let's draw some times here. So here's 5 seconds. What speed would I be going at a time of 5 seconds? Well, I would still be going 2 meters per second. At 10 seconds, same. At 15 seconds. So this is constant speed on a velocity time graph. We are moving in the forward direction at constant speed. And we have a horizontal line. So when you see something like velocity is constant, it is a horizontal line on a velocity time graph. Having done that one, let's look at the next one. Here we have another one with uniform motion. That means constant speed. We're moving forward again, which means the speed is positive, and we're going fast. So we're going to have to change the scale of this graph. So let's make all of our labels. Velocity v, that's meters per second. Time t, that's seconds. And really we can make the graph about the same size. All we have to do is change the scale. So let's say this line is 5, this line is 10, -5, -10, here's a 0. There's a 0 there. So if we want to say moving fast, I would say 10 meters per second is somewhat fast. So we start at 10 meters per second. After 5 seconds, what's the speed? 10 meters per second. After 10 seconds, 10 meters per second. After 15 seconds, 10 meters per second. So again, we have an instance where velocity is constant because it's uniform motion. The velocity time graph is a horizontal line. The only way we can tell that this one is fast and this one is slow is the difference in the scale. This is the importance of scale. If we took away all the numbers, these graphs would look almost identical, and the data would really not do anything to help us. Next one, C, at rest, at home. Let's go ahead and draw the graph. So something you might remember, at rest, you technically have a speed. Your velocity at rest is 0. So I'm going to do this one in a different color. I'm going to use red. Here's my velocity, 0 meters per second. 5 seconds later, here it is. This is my velocity. This is my velocity. And so this graph shows me at rest. It also says at home. Can I know my position based on a velocity time graph? There is nothing on here that would really imply where I'm at. So if we want to know about at home, I'm going to use a different color here. If we want to know about our position, we have to use the distance time graph. So distance, meters, time, seconds, and here's 0, 0. At home would be here at a distance of 0 meters. This is at home. And so at home, I'm not moving anywhere, so I'm still at home. Time passes on, still at home. This is the only way I can really know my position or my location, meaning at home. So to illustrate this, let's look at the next example, D, at rest, anywhere. So the first thing, at rest, remember our velocity is 0. So let's go ahead and set up our velocity time graph. So we're at rest. Our velocity is 0. So at the beginning, if I'm at rest, I'm not moving, my velocity is 0. I'm still not moving, I'm still not moving. This whole time, my velocity is 0. So the velocity time graph looks exactly like the velocity time graph from example C. The difference that we're going to have is that this one says anywhere. Anywhere means we don't have to be at home. So I don't know my position based on this velocity time graph, but if we include a distance time graph, like we did, if we use a distance time graph, then we know position. And let's say 5, 10. Let's make up a scale. So anywhere. Anywhere could be whatever you want, but I'm going to say it's 10 meters away from home. So I look up at here, here's 10 meters away from home, and I'm not moving. So as time passes, I am just sitting 10 meters away from home. Never getting closer, never getting further away, and I can label this. This is anywhere. This is my representation of anywhere. E, uniform motion. That means constant speed. At this time, we're talking about backwards. Uniform speed moving backwards. Label the graph. Here's 0, 1, 2, -1, -2. Moving backwards is represented by a negative velocity. So let's say I'm moving 2 meters per second. That could put me here, or it could put me here. But we specified that I'm moving backwards, so my velocity is going to be negative, and it's a constant speed. So at every point on this line, I am going to be moving at -2 meters per second. So this is what my graph would look like of uniform motion moving backwards. Using the basic velocity time graph, we can arrive at a new physics definition. This is the definition of acceleration. I'm going to write the definition here. Acceleration is the rate of changing velocity, or put maybe another way, how quickly velocity changes. Formula. Acceleration is represented by lowercase a. Acceleration is, take a look at this, we have velocity and we have time. Looking at the slope of a graph, remember rise over run. Change in velocity is the rise. Change in time is the run. So really, and based on time, we can just make that t. Acceleration is the change in velocity over time. Or written another way, acceleration equals velocity final minus velocity initial over time. Final velocity minus initial velocity, how fast velocity changes, divided by time. And here are your two formulas, basic formulas for acceleration. If we were to draw a graph over here, here's velocity, here's time. Here's one known point, here's two known points. This is the rise, this is the run. They are at right angles. That's my delta t, change in time from this point to this point. And this is my delta v, change in velocity from this point to this point. And that's how we arrive at the formula acceleration equals delta v divided by delta t. Let's go ahead and write in a few little definitional pieces. Vf equals final velocity. And let's maybe even label that here. Vf. This point is what we're using as Vf. It looks like we continue to speed up, so your final velocity could be somewhere above as well. Vi is initial velocity. So this is our initial velocity as far as the slope was concerned. If you're stopping at a stop sign, your initial velocity might be here. But as far as our slope, this was initial, this was final. So let's talk about feelings. What do you feel as far as speed or acceleration? Feelings. You don't feel speed, you feel acceleration. Think about it. If you sit in your car, it's parked, the velocity is zero, it doesn't feel like anything. If you're driving down the highway smoothly at 55, it doesn't feel like anything. If you're driving at 30 through town, constant speed, no bumps, you don't feel anything. You don't feel speed. What you feel is acceleration. When you start from a stop sign, you feel the acceleration pulling you backwards. When you're coming to brake at a stop sign, you feel the acceleration. You feel changes in speed. You don't feel the speed itself.